right, well, welcome to Western Michigan University. My name is Steve Budden. I'm the Dean of the College of Engineering and Applied Sciences. I'm also a professor in industrial engineering, as well as the great term entrepreneurial engineering. So it's a pleasure to be with you today. At this college, we are known for innovation through hands-on learning and an entrepreneurial mindset. Our faculty create opportunities for students to build, test, and experiment. So learning is always connected to real problems and a real impact. As a result, our graduates are career-ready, innovative, and adaptable. They bring a true can-do WMU mindset, taking initiative, building what's needed, and being prepared to make an immediate difference in industry, research, and their communities. All right, so it's now my pleasure to introduce today's panelists who reflect innovation, collaboration, and applied impact that define the College of Engineering and Applied Sciences at Western Michigan University. So first, I've got Dr. Kristina Lemmer. She is professor in the Department of Mechanical and Aerospace Engineering and the founder and director of WMU's Aerospace Laboratory for Plasma Experiment, or ALPI. She also leads Western Aerospace Launch Initiative, where she's mentoring students through the complete satellite missions lifecycle, from design and testing to launch and operations. Next is Dr. Mert Atilhan. He is professor in the Department of Chemical and Paper Engineering and director of the Thermodynamics for Energy and Environment Lab. His lab integrates molecular simulation and experimental methods to address challenges in carbon capture, gas storage, and sustainable materials. Dr. Claudia Fajarado is a professor in the Department of Mechanical and Aerospace Engineering and the director of WMU's Center for Advanced Vehicle Design and Simulation, also known as CAVITS. Her research focuses on turbulence, combustion, and energy conversion systems using advanced non-intrusive diagnostic techniques. Dr. Sandru Kuruppu is an associate professor in the Department of Electrical and Computer Engineering and the founder and director of WMU's Transportation, Electrification, and Applied Mechatronics Systems, or TEAMS Lab. His lab focuses on power electronics, electric machines, and electrified transportation systems. And finally, Mr. Jim Castellano, who is a proud alum and the chief advisor of electrification engineering at Astemo Americas. He earned his Bachelor's of Science degree in automotive engineering from Western Michigan University and began his career at Ford Motor Company. Building on a strong foundation in traditional automotive engineering that has evolved into more than 4 decades of leadership in electrification and high voltage battery systems. Welcome to you all.
Cindy and I will alternate questions between the 4 following areas. The first is the future of university academic programs. Then a focus on activities and student organizations. And after that, we talk about industry-university partnerships. And finally, some of our favorites, hands-on experiential learning. All right, so we're gonna start with the first section, which is the future of university academic programs. And we're gonna start with Professor Mert Atilhan. How do you bring real-world practical engineering problems into your classroom to better prepare students for the industry?
Okay, to me, right? Yeah,
Yep.
Okay. It's very important to integrate the real-life problems into the classroom setting because, for example, in my case, the chemical and paper engineering, the context might get so heavy and so math and science oriented. However, when you take your degree and start working in industry, you see all different types of different problems that are not directly coming out of the textbook. So I started talking to recent alumni. They are within the 5 year of their graduation. So those quote-unquote fresh engineers, so I asked I make a survey, I give them a survey. So they were not necessarily my old former students, but also some folks that I get to know through the field trips or collaboration visits, etc. So I asked them, what was your immediate problem that you faced when you were 2 months 2 months old in the firm that you're working at? So I have a list of problems that I see that it was a problem for them, and they're real life problems. So I bring them to the classroom, but the students they don't know that these problems are coming from the real life experiences. So and this happens mostly in the junior senior level classes. For example, they design a heat exchanger, or they design a mass exchanger, or a separator column, and things like that. So as they know enough physics or math of how to solve and design this engineering problem, I start feeding them with these kind of real life problems through the homework, through the project sometimes, and some open-ended problems. And towards the end of the semester, we always have inquiry guided based sessions. Like we call them mini inquiry sessions. I drove a real chemical engineering plant and a real problem that we commonly face with. Then I start asking, why do you think this is happening? You have 60 seconds to come up with this solution. I'll be walking through the aisles, then I'll be taking your questions. If you use your question, ask. If you don't ask, you lose your chance to ask. But at the end, I'll need half a minute elevator pitch from each group. And it keeps going on with the increased level of intensity, and these are real problems, real life problems. So getting to know the fresh engineers within the 5-year graduation mark, knowing their problems when they started their careers, I recycle that back to the existing students, so it helps their lifelong learning. So this is typically what I do in the classroom to connect with the real life problems. Obviously, need to say, I'm sure all the other panels have the same viewpoint about the emerging technologies. So we might have different questions coming up, maybe like the inclusion of machine learning or AI. So I don't forbid them, but I don't encourage them at the same time. So it's a delicate balance. So as long as they use it with the in a responsible way, which is very hard, to be honest, to check. It is okay to address the real life problems through the through those tools, emerging tools.
Sounds like a very good process. The bottom line is you have to put the two together, and if they don't know how to use it, what good is it, right?
Yeah.
Thank you for that. Dr. Kuruppu, engineering needs to be applied in many cases, okay? How do you enable students to experience this through your courses?
Okay, thank you. Yes, thank you, John. Now, if you, so I teach controls and power electronics, and a combination of those courses. And if you think about from an electrical engineering point of view, or any engineering point of view, it has to be practical. And I think there are a few students who have taken my courses, and I try to make them close to real engineering. So the way I decided, how the approach I had in selecting or framing those courses was I kind of looked back how I learned. So I was in the industry for a while, in the automotive industry and the semiconductor industry. And there, when I graduated and started working, it was not that easy to get started with what the industry was expecting. So there was a lot of mentoring from the senior engineers that kind of got me there. So I started bringing that into the classroom. So now they have a real industry-related problems in the classroom that still uses what you learn in the classroom. So I teach a linear systems course as well as electric vehicles and hybrid electric vehicles course. In the linear systems course, they're basically learning about how dynamic systems work, how they model. So we bring in a problem like designing an elevator control system, designing an escalator control system. And then they get real parameters. They get real requirements. You have to meet these criteria in developing your solution. So they would go characterize the plant, develop the solution, verify the solution, which is part of what you would do in industry in a practical application. And then same with the EV, HEV course. So we build basically a model of an electric vehicle. We initially start with very simple formula. We look at, how do we simplify things so that the model will run faster but very coarse results. But then we start adding details, because as you go through the course, you're going to learn, what does the power converter do? How do we implement a motor model that would give you the exact results or close to exact results you want? So we complicate part by part while keeping the overall vehicle model the same, and then we would subject it to real or close to real drive profiles. And then we evaluate efficiency, evaluate performance. So this way, they get a snapshot of what they would do in the industry, and that can build on what they learn. So they take that with them, and now they can talk about it. Even if they go to like an interview, they can say, hey, look at this paper, this is what I did, this is how I designed it, this is what I used in doing that design. So that's how I approach that.
So it's not just the answer, it's the whole process to getting to that answer that makes a difference. Also, if anybody wants to jump in on any, if there's something you want to add, please feel free to do that. Jim Castellano, what do you see as quote unquote systems engineering?
Yeah, thanks, John. In the automotive industry, things have evolved from traditional electrical, mechanical engineering, chemical engineering. It's really much more a system approach. When you join in and start to do the programs on a vehicle, it's how to integrate the hardware and the software together. So what you find is a very collaborative approach. So where traditional mechanical engineering maybe did packaging, maybe thermal on a module, you're now integrating this module with the topology of the vehicle, the wireless controls, so the electrical engineering elements and features you develop together. And the engineering background you have is broad enough in many cases where you can blend over between mechanical, electrical, and even chemical in the automotive field. So we see that as a trend, that you have to be open-minded and understanding the space is changing. And it's more a system approach and collaborative approach that we're seeing.
Gotcha. Dr. Lemmer, engineering curricula has traditionally been built around theory and technical depth. But AI is quickly shifting how students learn and how engineers do their jobs. What are examples you are using in your class to meet the demand of AI?
Thanks. So this is happening in real time, and we're all trying to figure out what this means for our future engineering jobs, for our roles as professors. So one thing that I think is incredibly important for the students is to learn how to use the tools and to learn how to interpret the tools. Mm-hmm. So I have a space propulsion class where I traditionally ask the students to design an in-space propulsion system as part of their final projects for the class. This semester, I have asked them to use AI tools to do that design, and then they have to interpret how well the AI tools completed the design. This is real-time learning on my part and their part, so we're figuring this out together as we go. But I think it's incredibly important for students to learn how to use the tools, learn how much they can rely on the tools, and learn to interpret what those tools give us.
I have a question to ask you. So when they interpret, have they found little glitches, or have they found problems that AI said would work, and then they decided there was a better way to do it?
Hopefully. We're in the process right now. The project is due at the end of the semester, so we're going through it.
I was hoping there was one that snuck in before this.
Yeah, so the idea is these AI tools can do a lot, but they can't do everything. And there will be glitches, and there will be incorrect answers that the AI comes up with, and it's up to the students to find those and respond to those.
If we could only teach the entire world that they can't, don't trust it, test it.
Exactly. It's coming real time, though. That's a fact. Kristina, I had one other question for you. What tools are necessary for students to learn to take advantage of the shifting AI landscape? What has been slow to change in engineering curricula?
So I think it's still vitally important that our engineering students get the theory and the technical background, because we have to understand that and be able to interpret the AI results that come out of these chatbots or systems. I think traditionally, as faculty, we know that that's really important to have those skills. And I think we are slow. Some of us might be a little slow to adapt to the changing landscape. Trying to figure out how to say this. How do we, if we are not teaching the students how to use these tools, then we are doing a disservice to our students. And that doesn't mean that we neglect the technical rigor and the theoretical background, but what it does mean is we have to figure out as faculty how to incorporate all of it together. And it's an interesting time trying to learn this and do this, like I said, in real time.
It's very interesting in every field. I mean, this is happening across the board. If there's anybody else who wants to chime in on that, please feel free.
Just to add Kristina's comment, we need to do the service to our students. I agree. I read an article that shows how responsibly we should be doing this, because I believe it was published in Harvard. I can't remember the journal. It was a very respectable, reputable journal. For the first time in history, the generation that is the alpha generation. I don't want to point fingers or put any generation on the spot, but their collective intellectual capability is not surpassing the one that is coming, that came previous. So if we don't teach the ABCs and the fundamentals of what we know, then at the same time we're not preparing them for the some disastrous scenarios. Again, I don't want to sound negative, but what if this happens? What if that happens? So what if we have a 4-day of power outage? So without having AI. AI makes it incredibly efficient and fast, but at the same time, you need to have the skills and ability to run them by yourself. So we have to do that service, but it's happening right now, as we speak. I don't think anyone has a correct answer to that. How to balance it out. So we'll just learn along the way.
That's almost to be continued, right?
Yeah. All right, this is for Dr. Fajardo. How does student involvement in technical extracurricular activities increase the value of the engineering education they receive here at Western?
Okay, so I think especially for our students that come in at the freshman, sophomore level, right, when you start in the classroom, they're used to very well-posed problems from the textbook, right? You solve them. You have the ability many times to verify your answer in the back of the textbook or whatever. But in real life, things are not that easy, right? So there's no textbook problems in real life. So I think participating in extracurricular activities, for example, here at Western, at the College of Engineering, We have the solar car program, the Baja SAE, Formula SAE, Aerospace has also, programs that students get involved in. And I think that is such a, fruitful way for students to be exposed from the get-go at different levels. Like when they start, they don't have to take on, they don't have to be the leader of the suspension team or the engine team. They can start, at a very basic level, but looking at problems, design problems, for example, that are tied to a practical system, right? And I had the privilege to advise the Formula SAE team shortly after I joined Western, and that was just an incredible experience to see the students take it from conceptual design, right? They have some guidelines that they have to adhere to analysis, to prototyping, to testing, manufacturing, right? Retesting. And then when they actually go out to competition, just to see them encounter those challenges, real life challenges, right? And work in teams to troubleshoot, to problem solve. I mean, those are things that you're not going to get. I mean, as much as we try to bring that experience into the classroom, participating in an activity like that is just a priceless way for students to really see that firsthand and apply what they've learned, right? And then develop new knowledge and new skills. So I think that's extremely important.
We had students at a different engineering college who commented that when they were in competitions, not only were they solving their own team's problems, but if the team across the room was having an issue, they often just pitched in and everybody worked together.
Yeah.
So it's a real team, whole team.
Yeah, the collaboration is incredible because you think this is a competitive environment, right? They're competing against each other, but yet they're helping each other. Like if I have a part that you need, maybe the Australian team is going to come to your rescue. If you need something, maybe there's something that Western can offer to help you get, so it's friendly competition and they're all learning from each other, and that's just a wonderful experience, but extremely beneficial.
It's great. Thank you. This is for Dr. Atilhan. Considering your focus on paper technology and eco-friendly approaches, how do student organizations fit in, and how do you encourage students to move beyond memorization and develop strong, independent problem-solving skills?
We have a couple of student organizations in our department. We have a long history in paper engineering. We have Cylon, a very strong student group, and we have relatively younger chemical engineering student organization named American Institute of Chemical Engineers, AICHE or AICHE. So both student organizations, they have their own hands-on competitions or activities going on. And in the department, we only become catalyst to make that process more efficient. I'll give an example. For instance, like from the paper engineering side, in the last few years, some of the students were working towards a competition, and the idea was having eco-friendly, biological, like forest products or paper products that can be used in batteries. So that replaces some of the existing battery components, and that could work towards the car, towards the electrical vehicle batteries. And they approached a few different faculty, me and a couple of, I saw them in the back. So we open our labs, they come, they meet with our PhD students, they meet with our postdocs, and they work together to solve a real life problem towards a more sustainable or eco-friendly solutions. And the other group from the chemical engineering perspective, so they are working for like how to come up with vehicles that runs with, let's say, hydrogen or methane or natural gas. But storing them on the board is a big challenge. So they are working on how can we store this safely on board, maybe like autonomous cars, autonomous drones, drone ships, and things like that. So how it's obviously when it's undergrad, it is not really very research oriented. It's more like kind of high level research going on their end. But they have fantastic ideas, and they bring this back to the discussion, roundtable discussion. So very fantastic ideas we hear from the student groups. And from the student organs perspective, they're doing a fantastic job, and we are only, pushing them to take the extra mile and being the catalyst for them. Yeah.
I can imagine it's not too difficult to get them to think outside the book and to get into a group of students who are problem solving on. And at any level, any team like that is bound to create better results and camaraderie.
One example, so a few years ago, when one of our team was competing in a key organization event, so there were like 48 teams, very similar to your example. We were having trouble with some chemical. For some reason, we didn't bring with us, so the camaraderie, not only within the team, but also the other teams. So a Polish team came to our rescue, shared the chemicals, and we were able to continue with our process. That was a chemicar. But you see them. I see them from a distance. They come up with these ideas that I cannot come up with. They really think outside the box. I saw the classroom. It is just fantastic to see, when you give them the opportunity, and thanks to the college and the university, obviously, so they also fund them and support them. So they come up with these all fantastic ideas. And I also see how they translate the basic knowledge in the class into something that can be applied in real life.
I mean, if I can add to that, so it's again applying what they've learned, and then also how do you approach a problem, right? Because that's not very easy to teach in a classroom, especially if something that's new, they are seeing it for the first time, right? And as they go through that process a couple of times, they figure out, okay, if I have something like this, what are the aspects that we need to think about, right? So that's also a valuable lesson. Right?
Okay, this is for Dr. Kuruppu. How important is your network that you create, regardless of academia or industry? And relate this to your work as founder as the let's try again. As founder of the WMU, Transportation, Electrification, and Applied Mechanics Lab.
Yeah, thank you. Yeah,
that's a mouthful.
Yeah, right. So in short, we call it Teams, Teams Lab. And I think it kind of weaves very into the discussion that we've been having, right, with Claudia and even with Mert. So you learn to work with, there are so many aspects that you kind of create as you go through these different team-based projects, team-based activities, because our population is diverse, right? There are different characters that we see, which you're going to see a cross-section when you go work in the industry, when you work in a industrial scale in a different team, right? So now you start learning about these characters that you have not seen before, right? And then you learn, how do we work towards the same goal, understanding the differences, right? So I think that's a valuable lesson. And another big lesson that we need to learn is that our network is very important. And I continue to share this with, any junior faculty, any colleagues, or any students that I meet from my experience, because I think that's a lot, very important for your career as well. So just to draw from an example, when I was finishing my graduate work and getting ready to graduate, I attended a conference, and this was a while back. And then during the conference, we were helping out, the conference, a bunch of graduate students. And over time, I see these individuals showing up in my network through different programs. So in industry, in like through IEEE, through projects. So eventually you meet your old friends back again, kind of full circle, right? So again, and they can also help you grow. You get ideas, especially when that's the purpose of going to a conference, right? You network, right? You make connections. So it has a big role to play in your career, in the work you do. And from project's point of view, it has been very helpful. So knowing, whom to talk to when you have a challenge, depending on whom you talk to, can help solve that very quickly. So I think it's very important.
Thank you. Dr. Lemmer, you're the founder of ALPI, the Aerospace Lab, as well as WALI, the Western Aerospace Launch Initiative. Can you tell us about your recent space activities? And related to that, what skills and tools do students gain from students' organizations at Western? Are these experiences that a classroom is unable to replicate? And I think we pretty much answered that last part already. It's important.
Yeah. So we'll start with my recent space activities. We at Western, we just launched our first payload into space. So it's super exciting. So it was a rideshare payload launched out of Vandenberg on a Falcon 9 on Transporter 16. And so far, so good. There's good communication with it, or so I've been told. So it's a partnership with an industry. Near Space Launch down in Upland, Indiana, and they reached out to me and my Western Aerospace Launch Initiative team to see if we could develop a payload to put on a thin satellite. And a thin satellite it's very small. It's 10 centimeters by 10 centimeters by 5 centimeters is the size of this satellite. And we designed, built, tested, and integrated the payload into the satellite. And the payload is a probe that is supposed to measure both spacecraft charging and the plasma environment in space. And so it was part of the WALI team as well as the senior design team that designed the payload. And then members of WALI built it. And we have a graduate student who ended up working on the final design, doing the testing and the integration. And it launched last Monday, so a little bit over a week ago. And the graduate student went out to the launch, and he has excellent pictures and photos, and
Wow.
It's really exciting.
That's incredible.
And yeah, so this is an experience that we wouldn't be able to get in a classroom. Kind of one of the really special things about WALI is the development of space systems engineering, that we don't teach this kind of these ideas and concepts in the classroom. So we have different subsystems for a spacecraft, and they have to work very closely and integrated together and come up with how the communication system is going to work with the payload structure, is going to work with the attitude control and determination system, is going to work with the thermal engineering, and the complicated issues that you have with any combined systems engineering problem are just multiplied when you go into space, and you can't have your hands on it to fix anything, or if there's a thermal problem, you can't just add some thermal tape or increase the conduction or the convection right away. So all of these teams have to work very closely together. And then we also develop leadership skills in our students, because we have a program manager who keeps all of the teams moving forward and develops those leadership skills. And we have a project or a lead engineer who makes sure that all of the subsystems are working together so that, you know, the person who develops the payload and that payload fits in the structure and doesn't take up all of the structure, because you also have to put in the power subsystem. And your payload can't use more power than the power is capable of producing. And so all of these systems, and it's complicated, interconnected systems that we don't.
So do you run lots of simulations and what's the other thing? Like a twin scenario where you're...
Digital twin?
Yeah.
That's the buzzword, the digital twin buzzword.
Yeah.
Yes.
I only got half of the words out there.
Yes, we use a lot of simulations in our work, and we're simulating the orbit of the satellite so that we can know how much sunlight is hitting the solar panels. We're doing thermal simulations so that we can, you know, make sure that components don't overheat or get too cold on the spacecraft. We're doing structural simulations and vibrational simulations and shock simulations to ensure that our payload can make it through launch and deployment, and on with our simulations. And yeah, a big component of working those teams together and making sure everybody is communicating is documentation. And it sounds really kind of boring, but it's really important for teams to be able to do that and to document everything that they've done, because people will leave positions and leave their jobs in the future to move on to new opportunities. And you have to have, for projects that last more than a year, you have to have that documentation for the future students or your future employees, those that take over your positions. So that's also a vitally important skill that the students learn when they're doing these designs.
Thank you. All right. Do you have a particular student, someone that comes to mind, where that you can think of that his or her education here directly affected their professional identity?
So many. I have several students who were in Wally who have since moved on to work in programs at companies in the small satellite industry, who before they started with Wally had no idea the industry even existed. We every year go to what's called the Small Satellite Conference, and part of that conference is a large career fair. And so they get to interact with these companies. They learn what products they sell, what products they develop, what the companies need, and they will interview for jobs right there at the conference. And so I've had several students who have, you know, gone on to their future careers through Wally and the skills that they've learned. And we hear all the time from the employers that these systems engineering skills, this documentation skills, are things that they really need their employees to know and to learn. And anybody who can come in with those skills is a step up above other candidates.
So it's real world experience turning into real world careers.
Yes.
Wonderful. Okay, now a question for Mr. Castellano here. Given the focus on a balance between classroom and non-classroom, what do you look for when you're interviewing and reading resumes?
Yeah, thank you. The hands-on is so critical. When we're looking at the different candidates that have applied, one that have had real life experience, and we look at the ones that have been involved in the student organizations. If you're involved in the Sunseeker or Formula SAE or I think it's the Cement Canoe and Civils, don't know all the different ones, but as you look into that, we understand that going through a project like that, you're going to learn from the design to the application to the testing. There's failures, and during those failures is really where you learn to grow. How do we fix them in real time? And sometimes at the track or sometimes in the lab. So those skills of how did I do, what did I learn, you're not always going to get from the academic side. It's applying the academic tools, but then in the real world doing that. So when I'm looking at resumes or my team is looking at resumes, both when I was at Ford and now at Astemo, we really focus on who's been involved in different student organizations, what was that learning, and many times we'll sponsor events and have the opportunity to talk to the students directly. And it's just fantastic to do that. And I encourage everyone to get that, because that is a separator when you're going through all the different candidates who has this experience, who has this background. And it's the learning that goes on there of putting it all together.
Thank you. John?
Absolutely. Now we're moving on to university industry partnerships. I want to go with Dr. Fajardo. In what ways do industry-university partnerships, A, advance developments of next-generation automotive systems, and B, student learning and training in this area of university industry partnerships? Yeah.
Okay, so I'll speak to my experience directing the Center for Advanced Vehicle Design and Simulation, or CAVIDS. So this is a research center that leverages collaboration between industry and then our faculty and researchers and students at the College of Engineering, but also, we have opportunities to reach out to other colleges as well. And we essentially together collaboratively identify technical challenges within the automotive industry, and we tackle them together. And I think it's the aspect of collaboration, of sharing ideas, of brainstorming together, of perhaps our industry partners that may not have the resources to allocate to a particular problem. We can jump in from our perspective, and we capitalize on their perspective as we're collaborating on these technical challenges. And I think it's been very fruitful, very productive. The center has been ongoing since 2007, so almost 20 years. And we've tackled problems in many, many areas within the automotive. And I think recently, mostly focused on EV drivetrain development, creating the tools, the technology when it's not there. I think that's something that's unique of academia or university industry partnerships. If you need something, for example, we had a project where we were creating a model. So the model is a simplified version of reality, right? So you always have to test. We couldn't find the technology to test what we wanted to, just because it was very unique, very new. It was related to high-speed gearing and EV powertrains. And so we decided to develop that technology. Now, I don't think we could have done it by ourselves from an academic perspective, but drawing from the expertise and the experience and also the in-kind resources of our industry partners, we were able to collaborate, and this is something we'll be launching here within the next 3 months. So that's going to be, it's really, really wonderful. And then for the students, right, if you have faculty that are involved in collaborative projects with industry, you're really staying on top of things. You're staying on top of technological developments, what are the real problems, and then back to Sandru's point, those are things that you can take to the classroom, right? So now you're looking at a problem from the textbook. Do you really need to use this problem, or can you shape it a little bit better to make it more into something that is of practical relevance? And you'll see that the students respond to that. You can engage them better. You can give them real constraints. They're based on real challenges. And so I think it's a win-win situation. But being involved with the actual, with industry brings that richness, I think, to the faculty and also to the students. I will say one more thing. The students are directly involved in these projects that we work through with industry. So all of what Jim talked about and Kristina has talked about, and all of us here in the panel, they're involved at different levels. They apply first what they learn in the classroom, but then they develop new knowledge, right? So that they're forced to think outside the box. They collaborate, they communicate, they have a new audience, right? We bring them into the meetings with industry. So now, how do you present to industry that's different than presenting to your fellow classmates or to a business audience, right? It's a different way to communicate, and they get exposed to that. And bottom line, it really sets them apart. We hear from our industry partners all the time that, they hit the ground running when they get a job in industry. So very fruitful both ways. We're developing a model to predict gear scuffing. And this is a phenomenon that happens when the lubrication film between two gears, which gears you can find anywhere, like all your transmissions in your vehicles, they're gear driven. But in an engine, in a conventional IC engine, you're looking at red lines, maybe 5,000 RPM, but you hardly ever get there. You're usually comfortably running at 2,000 RPM. For the EV drivetrains, we're trying to push that. And so we wanted to test at 20,000 RPM. If you can wrap your head around that, that's a big problem, right? So we're trying to validate this model. We can't because we don't have the tool, because we don't have a machine that can run that high. So what do? You call around, right? The wheel's out there, you don't want to reinvent it. So you call around, you see what kind of equipment, test equipment is out there. There's nothing is out there. And if you buy one for $250,000, you're going to have to retrofit it to get to the speeds that you want. So that's the challenge that we undertook, is we actually developed that piece of equipment. And we've involved students. And at the beginning, the students is like, well, how can I possibly work on this problem, right? It's high-level tech. It's like, you certainly can, right? If you're a freshman, you can bring skills. If you're a sophomore, you can bring skills. Juniors, seniors, teams, graduate students, right? At whatever level you're at, you can contribute. We look for creativity. We look for passion for what you're doing, right? Dedication. Can you take ownership of a small task that is given to you? Because we're going to parse the big problem out into chunks so that we can get the help that we need to get it done. So it's a great opportunity, big challenge, but good opportunity.
It sounds exciting.
Yeah.
Dr. Atilhan, I wanted to ask this. In what ways does involving students in active, open-ended research give them a competitive edge in the job market? Is your Department of Energy work an example?
Yeah, great question. So we have, in the College of Engineering and Applied Sciences, we have quite many student activities, events, and one of the biggest, largest, I would call maybe flagship event is the Senior Design Day that takes place at the end of every spring semester. In a couple of weeks, we will have that. So in our department, we participate. All the groups of senior design projects are industry-sponsored projects. So the way we look at the capstone or senior design project have changed a little bit over the last few years. We have a good blend of open-ended research problems that are linked back to the what we taught them in the classroom settings, like design of a component of a system, which they were the research side of it during this experience. So we have seen quite many examples that our students who work with an industry-sponsored focal points, they were hired by them. This happens very frequently. I'm sure it's a common practice throughout the whole college. When students receive the first, in the first meeting, when they receive the open-ended question, the sponsors might or might not have an idea how the project will evolve. Sometimes it's just an assurance or making sure the approach on a new product design is going to work through the university research. Sometimes it's just like, hey, we don't know, we have an idea, let's go try together. So I like the second one better because it's unknown to everyone, and students, just an example, they would like to see how a new additive, chemical additive, improve the paper strength, or how we can come up with a new coating material that is not petrochemical based, that is natural based, that can resist some, let's say, that can resist moisture, but at the same time, biocompatible, food packaging compatible, etc. So things like that. So in those projects, students drove their constraints based on real life examples, real life constraints. So we have meetings going with the focal points from industry every week, sometimes twice. So they learn very valuable experience through those meetings with the industry partners that we can teach in the classroom easily. So it's a very dynamic, back and forth exchange of information setting that we have, and it's a great showcase to present those findings in the senior design day. So.
It sounds like it would be exciting for students to do that, the second one, because you're like, we're doing something that's more novel. It's not something, well, check this out. It's not that. We're trying to find a solution for something like that. That's great. Dr. Kuruppu, how can internships benefit both students and industry in a meaningful way?
Yeah, so internships, again, I think it kind of goes along the lines of practical experience, and how you would relate that to what you learn. And then from an industry point of view, the industry gets, a short term to evaluate the students, evaluate their capabilities. There is no commitment, they have a short term to do that. And then I think, in my opinion, it's more beneficial to the student, because students can actually take this and then they can try out different career options. So, and I actually recommend this to students, because you will, when you're doing electrical engineering or mechanical engineering or chemical engineering, there are so many sub areas, right? You never know where your passion lies, right? And there may be a case where there's an electrical engineer who has more interest toward mechanical engineering or even chemical engineering, right? So once you get exposed to a certain aspect, then you realize, oh, I like this area much better. It's not that you can't do the other parts, but you have, some natural talent towards that area. So when you try out, for example, I worked in the automotive industry, I worked in the semiconductor industry, and then I have also tried out teaching, and then, kind of helped me figure out what I like the most, right? So internship can be a very good vessel, a very good platform like this that would allow you to go explore, right? And go try out, go to different parts of the country, because some of the students I see that, hey, I just want to stay in Michigan. I want to stay in Kalamazoo, right? I mean, it's good, right? But you still need to go try out, what is it like to live in another place, get some different experiences. And now you will have a more informed judgment than a very narrow judgment. So that's how I look at it. And of course, there's the benefit to industry to evaluate different candidates and then see who fits better to their role.
That's cool. Well, I have a follow-up on that. What level of demand exists for electrical engineers in the current job market?
It's huge. I mean, and I can't, we looked at these numbers a while back. There were so many job openings for electrical engineers in Michigan by itself. I think it was about 400 or more several years back. And that means that, there are so many opportunities for you as an electrical engineer to, take up a career and then grow, right? I don't know about statistics related to other engineering fields. I'm sure they're similar, but if you take the country as a whole, I think there is a huge demand for electrical engineers who are capable, right? And so you wanna be able to, not just say, hey, I'm an electrical engineer, but I wanna be able to do something. I wanna be able to contribute something. So that means you have to learn, try, have the hands-on experience, and then be able to present that way.
Jim Castellano, how do you see the value of that hands-on experience?
Yeah, we talked a lot about, the co-op internships as a way of getting it, but the hands-on experience is really critical. Used to use the term practical engineer, whether it's mechanical, electrical, civil, joining chemical engineer, joining the company. We look for practical engineers, someone that was involved in and did projects or internships where they worked with a team, it's really important. The student projects are the other avenue I talked about earlier, where they just provide this ability to learn in real life, because we find out it's not a textbook solution. You come up, you develop, you fail, you regroup, you learn. And that's what we feel is really important, with the practical engineer leaving with some experience and then coming in and joining. There's an engineering V, you design, you go down, you test, you go up, and you finalize the project. Doing these projects and having that experience is really important. The other one that I really think, we talked a little bit about the capstone project. A million years ago when I was at Western, we still did the capstone projects. And we happened to publish ours, NSA, as alternative fuels. It was in the early 80s, and people maybe remember or read about gas lines. So we were looking at natural gas and propane, LPG as alternative fuels. And Canada was very big into LPG, so we presented our paper in a SAE in Canada. But that got you exposed to industry. And I do think that the capstone projects are a way of also tying with industry. We ask for industry involvement. And that ties nicely then, because you can have mentors helping the student or the team of students. You also collaborate. They're not individual, they're typically team. And in the industry, there is no more A, B, C player, right? It's a team effort. You're not going to survive without that. So learning that is really important. So the hands-on experience of not only doing a project, working with a team, and gaining success. Success may be actually failure, because you may understand we didn't get the end game, but now we know how to redo it and move on. So the hands-on learning is really important. And as I said, we kind of coined the phrase, we look for practical engineers. So.
And I'd like to follow up on that a little bit. One of the things that I think that the students get when they start doing practical projects is a lot of the theory-based classes and the technically rigorous classes, the problem solving is linear. Like, I do this step, and then I do this step, and then I do this step, and I get my answer. And one of the things that the hands-on experiential learning helps teach the students is that solving problems is not linear. You might have to come up with an idea, and then it leads you there, but then you realize that first part didn't quite work out the way you wanted to, so you have to circle back, and then you might make it a little bit further down the road, and then you have to circle back and readjust some parameters on your process. And so the problem-solving process, the design process is not linear, and that's something that the hands-on practical experience teaches students that, doing problems out of a textbook doesn't.
Yeah, and then also on that, which I completely agree with, is developing engineering intuition, which especially at the beginning, unless you've had an upbringing where you have been working on things and, just have that knowledge already or bring that knowledge to the table, is you get an answer. Does this make sense? Am I way off, right? Is this reasonable, right? And that's something that just comes, it comes easier when you work on projects and when you do the hands-on stuff than if you're solving problems from the textbook, because you're guaranteed the solution in the textbook, right? That you're gonna get it, right? And you're gonna check yourself. And so with that development of engineering intuition, then the students begin trusting themselves more. Right, so they try it, they may fail, but they will learn. And I think in that process, they both develop that engineering intuition, and then they learn to trust their process and become better engineers, I think, in the long run.
Yeah, I would like to add, though, one thing that, the professors do a fantastic job providing the students today with tools. And some of the gray-haired old engineers like myself, when we sit back and look at the young students coming in, from where we were when we started to what you guys have done a fantastic job. I mean, in many cases, it's like, the exposure, the tools they have are tools box that used to have to get at master's levels degrees, right? They're coming in with this depth of knowledge and skill set and getting the ones to have the practical experience to go with that, you quickly accelerate, because in that environment of team building and learning in industry, projects move faster and faster. You know, I started at Ford, it was 7 years to develop a truck and a car. When I left, 7.5 years ago, it was 3 years. It's now 2.5 years. So they've taken out 2.5 prototype levels of development, right? We now can do so much more with, simulation. You still have to develop, prove, and test. But we can do so much more with the modeling and capabilities that we've never been able to do before. And that's the same. So then industry's got to move. And, being an Astemo, a traditional Japanese company, test, find, fix, along with the modeling and skills and database, you've got to accelerate your process because you've got to be competitive in the field. So I do think, these tools of having the students learn that and move forward and then having experience gets them into that mindset very quickly.
What are the most effective ways for industry leaders to partner with universities to support this hands-on learning we're talking about?
Well, one, like I said before, the quickest, easiest way, the low-hanging fruit is through the capstone design projects. So they have a problem, and we have the resources, so it's a natural connection. It's out there, and it's practiced for decades, so it's very easy to continue build on that. So we are continuously seeking for new partners on different fields, like not only paper side, but also chemical side, or the chemistry side, or the materials design side. That's a platform that we are continuously growing as we speak. The other way is it's a homework for the faculty that keeping active on your toes on research and also opening your labs to the undergraduate students and also as well as graduate and the postdocs, etc. But and while you're keeping active in research, you also seek active collaboration with industry partners. So that's a symbiotic relationship. So both parties get big incentives out of that. But once you have industry involvement in a cutting-edge research project like Department of Energy, Department of Defense, NASA, or the National Science Foundation, so the inclusion of the students in those projects, and through working with the industrial support, that's the workforce that we would like to develop for the generations to come. So in those involvements with the industry through funded research projects, it also teaches students some other soft skills like responsibility. They have to deliver because it is assessed by a third party, and it also teaches them accountability. So these are the soft skills that our accreditors, ABET accreditors, all the college departments are accredited by ABET. It's part of the evaluation rubrics that we have to tick the boxes like lifelong learners, information seekers. So when it is only the research and the learning experience are only with the faculty, quote unquote faculty, sometimes it might get bone dry. There is nothing wrong with that, but it could be a bit superficial or a bit old-fashioned, let's say. But once it is carried to a platform that a government organization is involved through an industry sponsor or industry collaborator, that makes a very good triangle. So every party is now talking to each other, and at the end, students excel big time. So that's how I see that.
Great, thank you. Dr. Lemmer, everyone talks about hands-on experiential learning, and we've been throwing it up and down the table, and how important it is for student education. But how is Western making this a reality for your students?
Yeah, it's another one of those buzzwords, right? Experiential learning. Everybody's got it. I think at Western, we we're making it a reality for students, especially in engineering, through our capstone senior design projects. So every student has to participate in this capstone senior design, which is a hands-on small group learning opportunity for the students to design something. And it's across the board for all of the engineering programs. All of the students have to do it, and they, groups of 2 to 5 students, and they have projects ranging from purely simulation designs to full development of hardware to testing the systems and just gaining these wonderful skills. But additionally, we do have faculty who are quite actively involved in our student groups to make sure that the students are getting those hands-on experiences within those student competition teams or the other teams. An example that I have is every year my launch initiative students, my WALI students, they collaborate with the IEEE students and put on soldering workshops so that the students can learn how to solder. And that then plays a vital role when they come to their senior design projects, where they might have to be putting together instrument panels or soldering electronics together.
That's an art. It is. My father, as a child, my father built radios, and I just loved looking at the boards. They were so cool, and his work was so good. All right, next question is for Dr. Kuruppu. Engineers need to be adaptable, to change during their careers. How do you build that into a student to focus on the whole trip, lifelong learning?
Yeah, so I think that again falls, it kind of, you can gain that through the project experience and then these other experiences that you get at Western through student organizations and all that. Because you will, start as a, fresh engineer, as you go through your career, you'll become a mid-career, then, at one point you will become the mentor, right? So throughout those stages, as you go through college, as you go through your learning, you experience these different challenges that will make you who you are, right? So depending on how you approach those problems, you will take those lessons with you. And then as you get exposed to these projects, these student-based group work, it'll give you a certain exposure to some of these that'll help grow, that'll help you nurture some of the skills that you develop over time, and then you will carry that with you. So I think that's a key area, that's one way you can gain that experiences that you get exposed to. And then I think another part of it is having the right mentorship as you go through that career, right? And then being the right mentor or being a good mentor, right? That doesn't come easy. Being a mentor is very challenging. You can, because if you are, let's say you're part of the solar team, right? And then as a young engineer, you'll be doing some assistive work, right? But then when you are the senior engineer in that team, how do you mentor these young, new students who join the group effectively? So that's a skill that you're going to build. And as you try to do that, as you go through the process, it'll help you learn better. You're going to, because if you are trying to explain electrical theory to some students who don't know, you better understand what you are teaching. You better understand what you're explaining, right? So now you better sit down and understand that, and then you can explain that. So what I try to do, again, this is kind of going back to the classroom. I integrate this mentoring into the classroom as well. So they would be broken into different groups, and then they will solve the problem. And then as they solve these problems, they teach each other. So they kind of learn how to learn. So that, I think, is a big part of that.
I think there's a real adrenaline that comes from discovery and problem solving.
Yes.
And I can see that translating into a desire for lifelong learning. As my father, as a retired engineer, was not retired really because he was constantly reading and learning. And
Exactly. I think that motivation that will help you kind of pick up those skills as you go through, that's going to help throughout your career.
And it's exciting. It's so exciting. We know that you have multiple patents. Is that part of a contribution that engineers should make? And how can these new engineers help pay it forward to further the next generation of engineers?
Thank you for the question. As an engineer, and my patents are team-based, right? There's a group of us as we were working on hybrids for Ford for the first time when we did that project. As an engineer, there's nothing more rewarding than, I think, patenting your idea. It's a technology that you've brought into industry. Other people will use it. Whether the company uses it or sells it, it's just a great way for your work to be recognized. I also think that it provides, the ability to share that with industry so other people can build off those ideas. The first idea isn't always the best idea, so many people will build off that. So, as I've left Ford and have gone to Astemo, I used to make it a requirement for my teams that they had a file for X number of patents, and it's like, oh, why do we have to do this? And it was really to get them to generate new ideas and record them. Whether the patent was awarded or not is not the important part. It's getting them to think out of the box and drive that. And so yes, I think going through that process for me was very rewarding, as well as the other members, but it also develops intellectual property for the company you're with, but it stimulates other ideas. So I think that's an important aspect. Another area that I encourage new graduates to do is getting involved with different activities in the different clubs, whether it's SAE, IEEE, SME, any industry, because as you go out into those industry workshops or meetings, you're going to meet industry experts, and they're going to help you in your career. Join a subcommittee. Most of those activities have an entry-level fee for new graduates, which is pretty nominal. I mean, college is very expensive, I get that, and that's a really tough part. But getting involved in these industries provide then an avenue for you to meet experts, work in experts. The skill set you bring, the academia elements, help to write and lay the foundation of many of the different regulations that go on. When EVs have hit a little bit of a bump in the road, every industry goes through that. I've been involved in electrification now for 20 years, so the highs and lows. But along the way, there's new standards, new requirements, and every one of those activities are involved in doing that. Connectors in automotive world seem pretty simple. They're really complicated little devices. Involved in those, you get the intermetallics, you get the conductivity, the micro leaching of the different elements in these connector interfaces, and what does a sealed connector mean in a wet zone and a not wet zone. So all of these different committees, you meet different people. It really ties the system approach of mechanical, electrical, chemical engineering together. So I encourage you to do that and get involved in that. And of course, the last one is give back to the university. There's nothing more rewarding for the new students and yourself to come back and maybe participate in a club that you were involved in or get involved in a new club. But when a student can talk to you now as an active engineer in the field, it really gets them excited, saying, oh my goodness, you went here and you're doing that. And if it can't be Western because you're now moved on to, a warmer climate maybe, or just where your job has taken you with the industry you're involved in, get into a local university and give back. There's nothing more rewarding than mentoring a student. You were talking about, you learn the product because you learn from teaching. You can only teach what you know, but you'll be so well prepared, you'll surprise yourself at how well prepared you are coming out of school. And then giving that back, the lifelong learning continues on at that point.
Well, that pretty much concludes what we were talking about here.